Wait a second. All right, we have started recording, and for backup, I will do this also. Okay, let's start now. So we were discussing this problem, and as I have been saying repeatedly, the main thing here in most of these problems is to do the calculations correctly. Okay. Nevertheless, I mean, it would be useful for us to at least take a look at least the calculation of the centroid for a problem like this, for a particular cross section like this. So let me quickly go through it. I won't go into the actual calculations, but just like a variable sort of way, I'll try to do it. So what we are looking at here is a cross section like this. So this is the T cross section. Of course, it's an inverted T. This dimension here, let's call that T1. This height here, let's call that H. This breadth here, let's call that B. And this thickness, this dimension, let's call that T2. So T1 is for thickness 1 and T2 is for thickness 2. In this particular problem, those two thicknesses, T1 is given as 30 millimeters and T2 is given as 30 millimeters also, but in general, it could be different. So first, for the centroid, what do we do? So we are going to consider as our reference this bottom line. Okay, so with respect to this bottom line, we want to figure out the y coordinate. So you imagine that the y coordinate is pointing upward. Okay, let me just draw that thing. The y coordinate is pointing upward like this with reference to this bottom base. Okay, so that we will end up finding out the y coordinate of the centroid. Suppose you take the z coordinate along this direction, even without any calculation, because this is a symmetric beam, symmetric meaning it has horizontal symmetry about this axis with which this y line is contiguous. There is no point in calculating it separately. The z coordinate is going to be 0 for the centroid. Okay. Now, for the y coordinate, what we will do, we will consider this particular part as one component of the T beam and this particular thing as another component. So I'm dividing this cross section into two rectangles. One of them is this rectangle and the other is this rectangle. Okay, so first I will consider this vertical rectangle. So for the vertical rectangle, the area is H into T1, and then you tell me what is the coordinate, the y coordinate of the centroid of this rectangle with respect to this bottom base.
T2 plus h by 2.
T2 plus h by 2, as simple as that. Next, for the bottom rectangle, what is it? It is simply b into T2 times T2 by 2. That's it. Now this thing should be equal to y bar, where y bar represents the y coordinate of the centroid of this entire cross section, which means that the thing that this y bar must be multiplied with is the total area of this cross section, and the total area is nothing but HT1 plus BT2. So from this equation, you can find out the value of y bar. Now, regarding the second moment of area, because for this problem you have been asked to find out the bending stress, and the bending stress can be found out at different points. You have been asked about A, B, and C. Only if you know the second moment of area or the moment or the area moment of inertia of the entire cross section. So as per the theory that we have been discussing about yesterday, the area moment of inertia has to be calculated with respect to the z axis, such a z axis which is coincident with the neutral axis, and we know that this neutral axis must pass through the centroid. So it is like this, that in the first step of the problem, you are determining the position of the centroid. So let us say that the centroid is located somewhere here. Okay, this is the position of the centroid. So C for centroid. Next, you position your actual z axis. Okay, your actual z axis. So let's say that this was our y bar. Okay. So our actual z axis is the axis which would be passing through the neutral axis. This neutral axis is also passing through the centroid, and the y coordinate, the actual y coordinate, will be like this. This is our actual y coordinate. So the second moment of area that has to be calculated for this entire cross section with respect to this z axis. Okay, that is passing through the centroid. So you tell me how do you find out the second moment of area? You have done problems like this when you were calculating the moments of inertia for problems involving rotatory motion in physics back in +2. Okay. So for the I, again we are going to consider these two rectangles separately, which are together making up this T beam. So tell me, for the first rectangle, forget about this z axis and y axis for the time being. If we considered or if you want to write down the moment of inertia or the area moment of inertia, or the second moment of area of this first rectangle about its own axis, which is passing through its own centroid, what is the value? Yesterday we had talked about it a little bit. 1 by 12.
Discuss. I mean T1.
Okay, 1 by 12, the breadth of it times the height of it about that its own centroidal axis. 1 by 12 T1 h cube. But this is not actually the moment of inertia, the area moment of inertia with respect to this z axis in which we are interested. So what do? We use the parallel axis theorem, which you're all very familiar with. Okay, I will not discuss the parallel axis or perpendicular axis theorem separately. You all know this. So tell me, what is it? For the parallel axis theorem, I need to know the total area. Total area is of course h into T1 times the square of the distance between the centroid of that and the axis from which we are supposed to calculate it. So you tell me what is it? What is the distance between the centroid of this vertical rectangle and the z-axis?
T2 plus h by 2 minus y bar.
T2 plus h by 2. So T2 plus h by 2. So we reach somewhere here. Somewhere here we reach. Minus and then minus y bar. Is it not? Because y bar that is the distance we have calculated in the previous step when we found out the centroid. That y bar is with respect to this bottom base, and this t2 plus h by 2 is also with respect to this bottom base. So we are good. So this is square. Next, for this horizontal rectangle, the same kind of thing we have to do. So tell me, 1 by 12, this time b into t2 cube plus what? What is the distance between the z axis and the centroidal horizontal axis of this horizontal rectangle?
Y bar minus T2 by 2.
Y bar minus T2 by 2. Very good. And so this is square, but this has to be multiplied with the area of this rectangle. So that is B into T2. Okay, so this is the entire thing. You substitute the values here, you will get the answer. So I've already done it for you. I've written a little script for it. So let me take this entire writing app to that same place where I have done the calculations. So I'll put it side by side. So the thing is that the calculations are done here. I just want to show you for a few seconds. So you can see it side by side here. The exact same thing that I have done. Okay, so first I have, in this part, I have calculated the centroid. I've gotten this expression. And all this is done symbolically. Here I'm calculating this I. And finally, what I'm doing at this step is I'm just putting the values of this H, B, T1, T2. And of course, the value of M also is given here as 100 kilonewton meter that I'm putting. And finally, I'm getting these answers. Okay, so these are the answers for our centroidal position and the area moment of inertia. And finally, all I have to do is utilize the formula that sigma xx is equal to minus my by I that I have done here. And you can see that it kind of matches with these things. It's given as 122 MPa here. I'm getting as 121.92. Okay, so that's how you do it. The reason why I'm showing this in Python here is that I think it may be useful for you guys to prepare a little script for each of these common types of cross sections and keep it handy for the T cross section, for the I cross section, for the C cross section, maybe even for the semicircle, rectangle. Rectangle is very easy, triangle, these kinds of things. I mean, during an examination kind of situation, or maybe even when you are doing problems, why bother about doing these calculations repeatedly for each of the problems when you already have a script ready where you can just substitute the values and get the answer in a matter of seconds. Okay, so I think that's a useful thing that you can do for your future self. Okay, so let's get back to where we were. Okay, so that's it. Let me go to the next thing. The reason why I have put this problem, I'm not going to solve it at all. I just want to discuss one thing very quickly here, is that once you have managed to set up a script or done a few problems with the most common types of cross sections like the T beam and the I beam and all these things, you will see that many other problems will be set up in such a fashion that they can be considered to be made up of those basic types of cross sections as their building blocks. For instance, this cross section looks rather complicated, but you can quickly imagine that this may be thought of as being made up of one T beam here like this plus two rectangles. So in that sense, the solution of this problem and the calculations involved therein can be like kind of modulated. Okay, it can be broken down into modules which you are quite confident about individually. So once you have done a few problems and tested out your script for the T-beam, you know that it works and you can just put in the values here. With reference to this kind of a base, you can calculate the centroidal axis, and then with respect to that base, finding out the centroidal axis of these two things are also quite easy. So things can be broken down in a very nice fashion. Okay, you can have, more complicated situations like this also. Okay, so let me go ahead. This is almost the same kind of problem which we had discussed yesterday. So I am referring to this one, this particular problem. But there is a different reason which for which I have put this up. You see, you just read the question that the shaft is supported by a smooth thrust bearing at A and a smooth journal bearing at C. And again, the same kind of thing is given that if the material has an allowable bending stress of sigma level this much, determine the required minimum diameter of the shaft to the nearest millimeter. So it's just a question of first finding out the reactive forces here, finding out the bending moment diagram, finding out where the maximum value of the bending moment is all along this shaft, and then just to use the formula that sigma is equal to minus my by I. Please also note that this is a shaft, meaning that this has a circular cross section. Okay. The real reason why I have put this up is to bring to your attention something else. See, when we are doing these problems individually within the context of a particular chapter, it is very easy for us to forget the influence that our earlier studies may have had. For instance, this is a shaft on which some kind of a pulley is there or some kind of a gear is there, and you are exerting this 16 kilonewton force and this 8 kilonewton force not directly on the shaft, rather on this gear, which means that if you look at it from the end on view, it may be possible that the diagram looks somewhat like this. Okay, so this disk, this outer circle that I have drawn, this corresponds to this, whereas this smaller circle that I have drawn, it corresponds to this shaft. What I'm trying to say here is that perhaps it is happening so that the force of 16 kilonewton is being applied at the periphery of this disk, which may be representing a gear or some kind of a pulley, whatever. Now, if such a thing happens, you can immediately understand that there will be a torque which will be exerted on this shaft, meaning that overall, while it is certainly true that this force, this downward pointing force, will also be transmitted in the same kind of downward pointing force for this shaft, but at the same time, it would be wrong for us to not at least think about the possibility that there may be some kind of an extra torsion that is being exerted here. Okay, so in an actual professional situation, and certainly we will come across problems where we'll have to properly consider the influence of combined loadings taking place simultaneously. For those kinds of situations, you cannot get away by just considering bending stress. At the same time that you are considering bending stress, you will also have to consider the stresses, the shear stresses arising due to torsion. So that is the reason why I've put this up. Okay, otherwise there is practically no difference in terms of the mechanical concepts between this problem and that earlier problem we were discussing. Okay, it's basically the same steps. The calculation is different because the loading locations are different. The shaft cross section is different, but other than that, there is nothing. Just another point which I would like to bring to your attention is that you note that the cross section here is circular. Okay, Now for a circular cross section, there is absolutely no trouble in locating its centroid. It is the center of the circle. Without even doing anything, we know this. But what about the I, the second moment of area? What do you think it is? Suppose we actually have been given the diameter here. I mean, at least in terms of this d variable. Ultimately, we have to find out this appropriate d for the design of this shaft. But let's say that this d is known. Okay, what is the second moment of area of this shaft, of this cross section? Tell me. Or rather, tell me, how do you go about finding it?
So
Of
we
course, the
consider the
general.
equation of the circle and double integration.
Right, so that is always the generic answer. Okay, given any cross section, you can of course find out the second moment of area by doing this integration of y squared dA. That is certainly true, but I'm sure you realize that that's not why I'm asking this. Okay.
So we can consider disks of dx or dr radius. Sorry, the radius at radius r we can consider rings of thickness dx or dr, whatever.
You want to consider this kind of a small ring, like
Yeah.
an elemental ring, and then you want to cover the entire area, right? If you do that, what you are going to end up with is the second moment of area about this axis, which is coming out of the plane of the screen from this centroid. And what is that thing? That is not I, that is the J. Okay, so if you are doing that kind of a thing, you are finding out the J, which was actually relevant in torsion. And that we already know for a circle that J is equal to pi by 2 r to the power 4. Okay, so what you are suggesting, you are going to end up with this. But it is good that you brought this up. You see, using this thing, we can find out this. You all know this. You have already done this. Tell me how.
So can we use the perpendicular axis theorem?
Very good. Very good. Perpendicular axis theorem. So you see, we know the second moment of area, not this one, rather this one. This also is a second moment of area, except that this is about this kind of an axis, which is coming out of the plane of the screen from this point, the center. So the common name for that moment of inertia is the polar moment of inertia. Okay, so this is more commonly referred to as the polar moment of inertia, which we kept on using in our entire chapter of torsion. But we can very quickly remember what we learned during the perpendicular axis theorem, that see, we are interested actually when we are talking about this I for this kind of an axis. But because of the nice axis symmetry of the situation, it really does not matter whether you take this axis or you take this axis or you take this axis or you take this axis. About all of these orange colored axes, the value of the second moment of area, that is this, is going to be the same, which gives us a clue that perhaps if we consider the disk like this, and cleverly we consider only two axes which are mutually perpendicular to each other like this. So the second moment of area with respect to this axis will be I, and with respect to this axis is also going to be I, because we have just now said that about any of these axes it is going to be I. Okay, so with respect to these two axes also it is going to be I and I. But the perpendicular axis theorem, it tells us that I plus I, meaning this I and this I, they will together be equal to the second moment of inertia calculated about an axis which is perpendicular to the common point of intersection of these two things, meaning an axis which is coming out of the plane of the screen like this. Okay, which means that this is nothing but J, because you've already identified that as the J. So it is like this, that you have twice I is equal to J. But J, we already know that this is equal to pi by 2 r to the power 4. So therefore, I is nothing but pi by 4 r to the power 4. Okay, so you always don't have to go about doing long calculations. With a little bit of, thought, you can make your life much easier. Okay. Let us go to the next one. Okay, I'll come to this a little bit later. Let me come to this composite beam. So yesterday, when we were discussing our basic theory of this various things associated with a particular cross section, we had mentioned that provided the material is the same, we can utilize those two equations. Remember, so again, I am not going to actually put down the values and solve this problem. Rather, I will present to you the general method which we have to use and the general kind of considerations which lie at the background of solving these problems. Okay, once you get the hang of that basic understanding, you can just put in the values and do the calculations, get the answer. Okay, so I will utilize this space to discuss that background knowledge. So it's something like this, that yesterday we were talking about these two equations. Sigma x6 dA, that is the total force that is being exerted on a particular cross section, that is equal to 0. And the other one was that y sigma x6 dA, that is equal to minus m. Okay, what are these two things? These are the exact same things which were there in this second slide. Okay, I'm going back to our Monday's class. These are the two things. M is equal to minus integration y sigma x6 dA and 0 equal to integration sigma x6 dA. So if you refer to the detailed notes that we were discussing yesterday, you will see that it is primarily based on these two things, and of course based on certain notions of the geometry, the curvature and all those things, we were able to determine the formulas which are necessary for solving these problems. So we are again going to fall back on these two basic things. But this time we have to appreciate the fact that there is a complication in the sense that this cross section does not involve only one material. And there was a comment while I was developing the theory yesterday that perhaps the fact that we had arrived at yesterday, that the neutral axis must pass through the centroid, that is not going to hold if the cross section is not made of a single material. And I had said yes to that comment, that yes, that is not going to happen. And this is the part where I show you that, that's how it is. Okay, the situation is slightly different. But before talking about what is different, I would like to point out what is same. So even if your cross section is made of different materials, something remains exactly the same as before. There is absolutely no difference between a composite beam or a homogeneous beam as far as that particular aspect is concerned. And that has to do with the nature of the deformations. Because if you go back, let me go back quickly. I'm referring to this slide. You see, if you look at this thing carefully, or if you again replay the video with my voiceover yesterday, you will notice that nowhere in this entire discussion there was any mention of the nature of the material. Okay, there was absolutely no mention regarding the nature of the material, meaning that all the discussions that we have had yesterday, which ultimately led to this expression that the normal stress along the x direction turned out to be equal to the negative of the y location of of that particular point which we are concerned with, divided by the radius of curvature, this entire expression, it remains valid whether the material is homogeneous or not homogeneous, meaning it is, as a special case, it's a composite beam. So this epsilon xx is equal to minus y by rho. It is perfectly valid even though the beam may be not homogeneous, not uniform material. Okay, so let me come back to this thing. So it is an extremely important realization that epsilon xx is equal to minus y by rho. This is still valid for composite beams. Now, what do we do next? Well, we recognize that indeed the material properties of this aluminium or this copper or whatever other materials that may be present, that is certainly going to come into the picture the moment we start talking about the stress-strain relations. So when we were developing these theories, we had very quickly written down the sigma xx in terms of this epsilon xx by appealing to the Hooke's law. And we are going to do the exact same thing, except that today we have to write two different versions of the stress for the two different materials present. So what we'll say is that for the material 1, it is going to be E1, where E1 represents the Young's modulus of the material 1 times epsilon xx. So basically we have minus E1 y by rho. And for the second material, this is going to be E2 into the same epsilon xx, because epsilon xx is the same for the entire cross section. This is going to be minus E2 y by rho. What does this do for us really? Well, when you realize this, you can come back to this equation, sigma xx dA equal to 0. Integration sigma xx dA is equal to 0 can be subdivided. This entire integration over the whole area of the cross section, it can be subdivided as integrations over the area 1 and that over the area 2. Now over the area 1, which is just made of one type of material, you can simply substitute this one, okay, sigma 1. I think it will be less confusing if I just directly write this as sigma 1 and this also directly as sigma 2, denoting absolutely clearly that we are indeed taking these areas A1 and A2 over those regions where only one type of material is present. So this sigma 1 I can substitute like this, E1 by rho times y dA minus E2 by rho y dA. And again, now we are going to utilize the same kind of argument which we had used yesterday. So over a particular cross section, okay, or you can immediately understand this E1 is just a constant. It has no dependence on the y. This E2 has no dependence over the y. And when I say it has no dependence over the y, you have to understand that it has no dependence over the y as far as the area 1 is concerned, as far as the area 2 is concerned for these integrations. When we go back to this thing, if we were to write some kind of a generic expression involving the Young's modulus, then of course that Young's modulus is dependent on y. Okay, of course there are different materials. Now for this, E1 and E2 are constant for these two individual integrations. The rho is a perfectly constant entity for the entire cross section. So all of these things can be brought out of the integration, and this minus can also be just deleted. So it's E1 by rho integration y dA over A1 plus E2 by rho integration over the A2 area y dA. Okay, So effectively, this row can also be deleted. What we are obtaining is E1 integration y dA A1 plus y dA. Okay, because it is this expression which is valid, unlike the previous situation, we can no longer claim that the neutral axis is going to pass through the centroid. Okay, that can only happen if the ratio between E1 and E2 is equal to 1, in which case they can also be deleted out of this equation. And then the equation that will be left with will be such that it denotes the fact that the neutral axis passes through the centroid. But now, because this E1 and E2 are not equal, we have to conclude that the neutral axis does not pass through the centroid. Okay. However, this equation is very helpful for us because it provides us a recipe, a way, a method for finding out the location of the centroid. Okay, using this equation, you can definitely go about finding out the location of the centroid of this cross section, which is made up of two different materials. Okay, so that will involve a little bit of calculation, certainly, but I will tell you of an alternative method. Okay, that's a very, very useful alternative method. But first, let me provide to you the basic things behind it, and then I'll give you the trick. Next, let us talk about this row. Okay, we have conveniently deleted it from the previous slide because on the right hand side we had the 0, but that is just hiding behind a mathematical convenience. The fact remains that we still don't know the row in terms of known quantities for the cross section. Okay, we know that rho is a constant for that cross section, but saying thing like that is just, I mean, hiding behind some mathematical convenience. It's a constant. Okay, but what is the value of that constant? Who will tell us that? We have to find that out. So let's try to do that. The way we do that is by appealing to this equation, the other one. Okay, so you see the spirit in which we are moving is exactly the same as earlier for the general theory. All right, the spirit is exactly the same, just the intermediate steps a little bit different because of the presence of two different Young's modeling. So it's like this: y sigma xx dA integration over the area of the entire cross section, that is equal to minus m. Again, just like in the case of the previous equation, we subdivide this overall integration into two integrations, A1 and A2. So this is y sigma 1 dA. This is y sigma 2 dA. This is equal to minus m. Now all that you have to do is appropriately substitute this sigma 1, which is minus E1 by rho, into y. We already have a y here. So what we will be ending up is this E1 by rho y square dA. Similarly here, for the second integration, it is E2 by rho y square dA. And again, we fall back on the same kind of arguments that we had been discussing previously, that over this integration over the area of A1, E1 is a constant. Over this also E2 is a constant and rho is certainly a constant. So we may as well take this out. And please note that we have this minus, on the right hand side also there is a minus. So all of those, they cancel out. So this is E1 by rho, and we are left with this y square dA plus E2 by rho y square dA. Now you see, this is a rather nice thing. Why it is nice? Because you can immediately recognize that this particular entity is nothing but the second moment of area for this area 1, and this is the second moment of area for this area 2. So we can very quickly write this as A1 I1 by rho plus E2 I2 by rho. And now you see that this is giving us a method of determining the rho, the unknown rho, in terms of quantities which can be easily calculated. Why it can be easily calculated, this rho? Because at a particular cross section, either from the bending moment diagram or from other calculations, or if it is given to us directly, we know the value of this m. E1 and E2 will be provided to us, and I1 and I2 are purely geometric quantities which can be calculated for any given cross section. So this entire right hand side will be known to us, and therefore this rho also is now known to us. Okay, so we can determine using this earlier equation the location of the centroid, and next by coming here we can obtain the expression for the radius of curvature. So all that is left for us to do is to go back to this equation, sigma 1 is equal to minus E1 y by rho, substitute the expression of this 1 by rho from here, and we can obtain the value of this sigma 1 at different locations of y. Similarly, for the sigma 2, we have this equation, and we can go about doing the same kind of thing. So effectively, we now have a method, although it may be a little bit long, but we do have a method of determining the stresses individually in the two different materials which make up the cross section. Now, all of you may be suspecting, is this the method that you should go about doing? The answer is effectively yes, this is the method that you should be going about doing it, but there is an alternative procedure. This alternative procedure is what is actually provided in your textbook. This basic theory, this basic extension of the general theory, this has not been given in Beer and Johnson. Okay, I provided to you because this is the very general thing. Now I'm going to provide to you an alternative method, which is actually what is given in your textbook. And there is a nice trick. So I again draw this kind of a rectangle, the simplest of cross sections, and I understand that this one is material 1 and this here is material 2. Whatever I have said in the previous slides regarding this kind of a composite beam, it holds. But now is the trick. See, this trick is not necessarily going to help you reduce the number of calculations or anything, but it gives you an alternative way, an alternative perspective of looking at the same problem. But there will be an advantage to it, which you will see in a few moments. So it's like this. It's true that we have this expression sigma 1 is equal to minus E1 y by rho. The moment I write this, you see the value of whatever we have been writing till now. So even though we are developing an alternate method, it is based on the basic theory or the extension of the basic theory which we have been talking about till now. So we have these two expressions. Now is the trick. The trick is like this. Suppose you consider that this E2 is such that it is equal to n times E1. Okay, basically we are saying that we have been provided two values, we have been provided values of E1 and E2. You just divide E2 by E1 and find out the value of the ratio. So maybe perhaps this is coming out as 10 or 16 or 21 or whatever. Okay, it need not be in any integer or anything. Okay, completely free. Okay, just a positive number. So you have this value of n now. All right. Come back to this equation, sigma 2. Put this value. So far, so good. But now we want to change our perspective a little bit. instead of talking about stresses, which is not very intuitive, let us talk about forces. So for forces, all that you have to do is multiply this stress and this stress by their elemental areas. So the elemental force F1, it is going to be equal to sigma 1 times dA. That is going to be equal to minus E1 y by rho dA. Nothing special here. But for the dF2, you see the sigma 2 times dA. If I utilize this expression, something nice it will tell us. Okay, even when I write like this, you may not realize it, but let me write it just a slightly different way. Minus E1 y by rho, but now I will club this n with this dA. What is the implication of writing it like this? Implication is that for the dF1, fine, we are writing this in terms of the E1, but for the dF2, that is when we are considering this material 2, it is as if because of the presence of the material 2, what is happening is that if instead of the material 2, we had the material 1 also in this place. Okay, just imagine, okay, like a thought, you just imagine that instead of this material 2, if the material 1 were present, then the force that would be developed here, that would be the same kind of force that is actually being experienced due to the presence of the material 2, is actually the force that is spread over an area which is actually n times the original area. So it's a mouthful of words that I just spoke. I will repeat myself. So listen carefully once again. We are considering this material 2. Now we are imagining that we are replacing this material 2 by this material 1. The motivation is that we already have different ways, or we have done a few problems by considering different types of cross section involving the same kind of material with some complications in geometry. What we want to do here is we want to replace this material 2 by the material 1. So you cannot do that arbitrarily. You have to pay a penalty for that. That penalty is in the form of an alternative area over which the same force would be experienced. Okay, so this material 2 is experiencing some force. If you replace that by material 1, it cannot so happen that the force itself has changed. Then the physical truth of the situation gets changed. That cannot happen. So we are considering the change of the material from this material 2 to material 1 in such a fashion that the force gets exerted over an area which is n times the original area. The net result of this is that the section which was looking like this will now start to look like this. For the material 1, it is exactly the same as before. This is our material 1. But now, because of this factor n times factor n, the lower part over which originally the material 2 was present, when we are replacing it also by this, when we go from this 2 to 1, we are effectively changing the area. Okay, so this becomes our transformed cross section. This is referred to as the transformed cross section. The good thing about this alternative way of looking at the thing is that we are all familiar by now with finding out the centroid, the second moment of area, the stresses for this kind of a thing, for this kind of cross section. I mean, for this very simple example, it turns out that the rectangle transforms into a T-beam, into a T type of cross section, which we have just done. But for other types of things, you may end up with, so if you have a material which is also present up at the top of this, you will end up with an I-beam kind of thing. So those are the kinds of things which are familiar to us. Okay, and the good thing is that they're all made of the same material. So this transform cross section is done basically with the motivation of transforming the original thing to a cross section which is having the same material. Once you have done this, you can go about your usual business, find out everything, but at the very last step, okay, you have to go back to your original cross section. So when you do that, for the material one, there is no problem. For the sigma one, it is whatever you find out. Okay, you proceed by the same procedure as before, you get the sigma 1. But for the sigma 2, what you will end up as sigma 2, that will be, so for this region, the sigma 2, let's call this, so it's like this, that for this lower region, okay, for when going back to this kind of a material, the hashed region, when you want to find the sigma 2, you will have to multiply by the factor n. Okay, for this region. The reason is that you see the sigma 2 is actually df2 by dA, something like this. Okay, but what you have done now, you have actually done something like, you are actually doing something like df2 by nda. When you are finding out the sigma, so I should actually write this as sigma 2 dash. So this here is the sigma 2 dash, this here is the sigma 1, no problem. So this here is the sigma 2 dash actually. So in order to go from sigma 2 dash to sigma 2, you have to cancel out this factor n. That is why you have to write this as sigma 2 equal to n times sigma 2 dash. That's the reason. Okay, once you do that, the value that you obtain will be the actual value to write down, to put down as your answer for this material 2. Okay, so I know this may be a little bit of a topsy-turvy ride in your brain. So just think about it for a few minutes. I'm sure you'll be able to figure it out. And the best way of convincing yourself that you have actually understood is to come back to this thing and get these two answers. Okay, once you do that, you'll feel pretty confident about yourself. There is another very typical kind of problem which involves this thing. But since I've run out of time, what I will do is I maybe record a short video and share it with you. Okay, this is a rather important situation. There are many problems which can be formulated based on this thing. Again, it's just a trick, very specific kind of trick involved with this kind of a problem. So I'll discuss it separately. Okay, it is there in your textbook, just a one-page thing, but it's important. So I'll record a short video and share it with you. So all right, thank you very much, guys. Prepare well for the test. All right, bye. Please go to your next class.
Sir?
Yes.
Sir, in previous question, sir, while transforming the cross section, why we increase the breadth only for increasing the area?
Why we increase the breadth only?
Sir, means for cross section 2, we increase the area by sidewise, right?
Yeah, because try to think of it in terms of the second moment of area. We are doing these things with respect to the z-axis, right? Everything is with respect to the z-axis.
Okay, sir.
So you are referring to things which are about an axis which is like this. Okay, so the things have to be scaled in that particular direction, parallel to the z-axis.
Okay, sir. Get it.
Right. Yeah.
Thank you, sir.
Thank you. Please go to your next class.